Now that I've shown you what a redox reaction looks like, it's time for me to show you electrochemical cells. Now, you know an electrochemical cell when you see one if you see a battery. If I were to, for example, open this device up and put a lithium-ion battery in front of you, go, oh, I see that little sort of button that you've got sitting there. Or if you're ever used to AA and AAA batteries or D-cell batteries, or your battery in your car, that's another example of a battery. If I want to talk about that battery as an oxidation reduction process, I need to have some convention for the way that I talk about it. And that means I need to spend a little bit of time helping you to understand some of the terminology that's associated with that convention and to help you understand some of the signs that we associate with that convention. So let's go ahead and get started. First of all, we appreciate that in every electrochemical cell there is going to be a reduction that occurs and there is going to be an oxidation that occurs. The particular cell in which that reduction takes place, that particular cell in which the half reaction that is a reduction that takes place is called the cathode reaction. That's the cathodic cell. In the half reaction, which is an oxidation, that's known as the anode. That's the anodic process. When I was showing you pictures of electrochemical cells that I was trying to balance, when I was balancing redox reactions, I never said the word reduction as at a cathode or oxidation as an anode, but I could have. When I show you A becoming A+, I used to call it oxidation. Now I can call it the anodic process. I can say this is the process that takes place at the anode. Here, I can talk about reduction occurring and say the reduction occurs at the cathode. Anode oxidation, reduction, cathode. How common is it that that happens? Always. There is always a cathodic process. There is always an anodic process. Every time you write down a redox reaction, you're writing down a cathode reaction and an anode reaction. Now you might ask yourself, how can I remember these? And I have one really lame way I always do it. Notice that there is the letter C sitting in cathode and the letter C sitting in reduction. So reduction takes place at the cathode and oxidation takes place at the anode. This is always true. This is always true. Now, having shown you this piece of cell convention, we also need to appreciate the following about electrochemical cells. They can be cells in which the reaction happens, or cells in which the reaction doesn't happen. And suddenly, as I say this to you, you're having a flashback to thermodynamics. Because remember, when reactions happen, delta G is negative and K is greater than 1. When reactions don't happen, delta G is positive and K is less than 1. Well, we need to be talking about the electrochemical potential, E. And while we haven't taken a look at it to this point, I can tell you that when I show you a voltmeter, when I show you this value right here for a voltmeter, there's my voltmeter. What's being measured on that voltmeter right there is an electrochemical potential. That electrochemical potential that I've just measured right there is related to delta G and to K through a simple equation. And it will turn out that from that equation we find out that when E is positive, a reaction happens. When E is negative, a reaction does not happen. Now, we don't know whether a reaction happens or not except through experience, where we actually see it occurring. But once we've seen it occur, we know that the E value for it must be positive, and if it doesn't, if it's reverse reaction is what we're looking at, that it's negative. Interestingly, as I take a look at these cells right here, and I think about whether a reaction happens or not, a lot of that is going to be driven by a sense of whether or not the electrons are moving in one direction or in another. So when I draw this kind of loop right here, believe it or not, I can draw the loop such that the electrons are moving here out of the cell into the right, or I can just as easily imagine the reaction being written such that the electrons are going in the other direction. So having the electrons move to the right or having the electrons move to the left is how I distinguish E being positive or E being negative. And get this, once I've decided whether this is the cathode or the anode that I'm working with here, I can talk about the electrons moving through the external circuit to the cathode or through the external circuit to the anode. Let's see what the particular cell convention for that happens to be. I show you here this table of signs, and it's very simply something that you have to memorize. I can have two kinds of electrochemical cells. The ones that are called batteries, those are the ones where a reaction happens. They're spontaneous. We know that delta G is negative. We know that E is positive. We know that the reduction takes place at the cathode. We know that the oxidation takes place at the anode. We also know it's possible for a reaction not to happen. There's actually a very important famous name we give to reactions that don't happen. This is called an electrolysis process. These are reactions that don't happen as written. These are reactions that are non-spontaneous. Delta G is positive, E is negative. The cells are still cathode at the reduction, anode at the oxidation. We can talk about the flow of the electrons, and by convention, the flow of the electrons is always through the external circuit toward the cathode, as it's written. So when I show you an example of an electrochemical cell, as we see right here, if this is my cathode and this is my anode, then by definition, the electrons are moving this way. The electrons are moving this way. Now, the only thing that's left for me to understand is the signs, the sign convention. You know that there are signs on batteries because every time you go to the store and you buy a battery, if you look closely at it, you'll see that there is the place which is positively charged and the place that's negatively charged. Or you'll look at a battery like this, and you'll see the place that is positively charged and the place that's negatively charged. So we'll look at any battery ever. There's always the plus, there's always the minus. And the question you have is, what's the sign? Well, the answer is that that is what varies. The sign is what varies depending upon the kind of electrochemical cell you have. But this is how I always remember it. In a battery, the sign on the cathode is positive. In a battery, the sign on a cathode is positive. If the sign on a battery is positive on a cathode, that must mean that the anode is negatively charged. And, this is the key thing, the signs are reversed when a reaction is reversed. So if I have a process that is not spontaneous, then the sign on the cathode is negative. This kind of makes sense when I think about it. If I'm looking at my cell right here, and I'm talking about the reaction going this way, having a positive value as I come to my cathode, then if the electrons are heading in the other direction, that must change the sign that I have associated with it. Now, what that sign ought to be depends upon whether you're going to be the system or not. Are the electrons coming to me, and I'm viewing it as something receiving the electrons, or am I actually the electrons that are coming, and I'm asking about what experience I've had? It isn't our place to try to figure out why people decided that you would talk about it in the context of the system or the surroundings. Our only concern is to accept the cell convention. And the cell convention is that the positive sign is associated with the cathode. The way I keep this in my mind always is every time I'm walking through a Walmart or a Target or an H-E-B or whatever, if I see a battery, I always bend over and I look at it and I see the positive sign, I go cathode. So do that. And once you get that into your head and you can assign this particular box on my cell convention, then everything else follows suit because it has to match with it. If that's positive, that must be negative, and these signs are reversed. Summarizing then, when I look at electrochemical cell potential, electrochemical cell convention, I can have two kinds of cells, cells that happen and cells that don't, batteries and electrolytic cells. The sign for delta G is negative if it happens, positive if it doesn't. For E, the sign is reversed. It's positive if it happens. That's what I measure on my voltmeter, and negative if it doesn't. Cathodes are reduction, anodes are oxidation no matter what. Electrons always flow through the external circuit to the cathode, and then the signs are, as you see here, walk through an HEB, battery, positive, cathode, and then everything else fits.